Welcome to the Explainer. You know, every single day we interact with all sorts of different materials, and we totally take their forms for granted. But today, we're diving right into the fundamental physics and chemistry of matter, because the hidden rules governing all this stuff, they are absolutely fascinating.
Think about it for a second. Why can you easily pour a glass of water but not an ice cube? It is literally the exact same chemical substance, good old H2O. Yet it behaves in drastically different ways depending on its physical state. And this everyday mystery is exactly what we're going to solve today by zooming way in to look at the unseen, microscopic world.
Here's our quick roadmap to demystify matter today. First, we'll meet the three states, then zoom inside the particle model, add heat and energy to the mix, track the transformation process, and finally, unleash the power of pressure. Let's get right into it. Section 1. Meet the three states. Let's start with the macroscopic properties of the three states of matter that we actually interact with every single day: solids, liquids, and gases. So at a macro level, the differences are pretty clear-cut, right? Solids have a high density, their particles are packed in this really regular pattern, and they basically just vibrate in place with very low energy. Gases, they're the exact opposite. They have incredibly low density, they're completely randomly arranged, and they move rapidly in all directions because they are absolutely packed with energy. And then liquids, well, they just sit neatly right in the middle, kind of balancing those properties out. Now, one of the most common points of confusion here is the difference between shape and volume. If liquid properties ever seem a bit tricky, just remember this. If you have 1 liter of water, you can't magically change it into 2 liters. It is practically incompressible, which means it has a fixed volume. But you can take that exact same liter and pour it into a tall, skinny vase, or maybe a wide, shallow bowl. It effortlessly flows to fit the shape of absolutely any container it's in. Part 2. Inside the particle model. To truly grasp why these materials behave this way, and why they either maintain fixed shapes or flow so freely, we really need to zoom down into the microscopic particle model, which is also known as kinetic theory. The absolutely crucial point to understand here is that scientists use this model to simplify a highly complex reality. Instead of looking at messy atoms or molecules with all their intricate bonds, this theory just treats every single particle as a tiny, solid, perfectly bouncy sphere. It is just an elegant shortcut. It lets us visualize physical behaviors without getting totally bogged down in the deep chemistry. Think of solids as basically a tightly packed crowd, just vibrating and jostling in place. Strong forces of attraction lock them into this regular lattice structure, and that is exactly why a solid is rigid and you can't compress it. But in a liquid, those forces are a lot weaker. The particles are still touching, sure, but they are arranged totally randomly. It's much more like people sliding freely past one another on a really crowded dance floor. In stark contrast, gas particles are like completely isolated sprinters, just running freely in all directions. The forces of attraction between them are remarkably weak, which leaves these vast empty spaces. Now, you'll often hear that gas particles move randomly, but they don't actually swerve wildly around. They actually shoot around in perfectly straight lines until they inevitably smash into the container walls or each other, and then they instantly bounce off in a totally new direction. Section 3. Heat, energy, and movement. Now we get to introduce thermal energy. This is the ultimate catalyst that drives a substance to change from one state to another. This is where things get truly dynamic. You can really think of this process as an energetic escalator. As heat is applied, a literal chain reaction kicks off. The particles absorb that thermal energy and they convert it into kinetic energy, which is the energy of movement. So they start vibrating more and more intensely until their interparticle bonds stretch, weaken, or just break entirely. And that is what allows the substance to transform from a solid to a liquid and then to a gas. Just to give you a sense of scale here, when particles finally reach that gas phase, they are absolutely buzzing. We're talking moving randomly in all directions at astonishing speeds of around 500 meters per second. Honestly, just think about that for a second the next time you feel a sudden breeze or you instantly smell a scent traveling all the way across a room. Moving on to Section 4, the transformation process. We know the mechanism now, but what do we actually call it? Let's map out the specific scientific terminology used when a substance climbs or descends through these energetic states. Looking at the complete cycle, as we move up the energy ladder by adding heat, a solid melts into a liquid, and a liquid boils into a gas. But here's a really fascinating detail. During those exact moments of state change, the temperature actually stays perfectly flat. Why? Because all that heat energy is actively being used to break the bonds, not raise the temperature. And of course, if we reverse the whole process and remove energy, a gas condenses back into a liquid and eventually freezes right back into a solid.
Now, it is absolutely vital to distinguish between boiling and evaporation. See, boiling happens throughout the entire liquid at one very specific temperature. Evaporation, however, that can happen over a wide range of much lower temperatures. The catch is, it only ever occurs right at the surface, where just a few lucky particles gain enough kinetic energy to break free and escape into the air.
There are also some totally fascinating exceptions to this cycle. In rare cases, like with solid carbon dioxide, which you probably know better as dry ice, a solid can entirely skip the liquid phase and transform directly into a gas. This is a process called sublimation. And the reverse is completely true as well. A gas can turn straight into a solid without ever being a liquid, and we call that process desublimation or deposition.
Which brings us to our final section, Part 5, the power of pressure. Let's explore what happens macroscopically when we take these incredibly fast, high-energy gas particles and we manipulate them within a confined physical space.
Remember earlier how we talked about gas particles having huge amounts of empty space between them? Well, that makes them highly compressible. Think about pushing down on a standard bicycle pump. If you use a piston to decrease the volume of a container, you essentially trap the exact same amount of fast-moving gas particles in a much smaller space. So as a result, they start colliding far more frequently with the container walls. Every single collision exerts a tiny little force, and collectively, all those tiny hits sharply increase the overall gas pressure.
We've used the particle model today to explain everything from a melting ice cube to a pressurized bike pump. But all of this leaves us with one really important final question. Is this model actually a perfect representation of reality? Well, the truth is, no. It's really just a highly useful simplification. Real particles aren't perfect little solid spheres. They're actually complex atoms and molecules governed by incredibly intricate interactive forces. But you know what? That imperfection is exactly what makes science so thrilling. It leaves us with an entire universe of deep, complex chemistry to explore. So what unseen forces will we uncover next?